In this video, we will be covering the topic of solutions. This includes part of Chapter 6, one section of Chapter 7, and the bulk of Chapter 11. Here are the topics that we will be studying. A variety of key terms that we'll go through and define. We'll discuss how solutions form. More key terms. We'll be discussing factors that affect the solubility of substances, as well as a variety of calculations, some stoichiometry, and colligative properties. Let's begin. This first slide has a variety of key terms on it. A solution is a homogeneous mixture. That's a term that we've previously discussed. Something that is a homogeneous mixture is uniform or the same throughout. Salt water is a good example of a homogeneous mixture because the salt is dispersed throughout the entire solution. Solutions are known to have two separate parts. We have something called the solute and we have a solvent. The solute is always present in the lesser amount and it gets dissolved. And the solvent is present in the greater amount and it does the dissolving. Most solutions that we focus on are aqueous solutions, okay, because they include water. So the term aqueous, also reviewed from a previous PowerPoint and previous presentation, is symbolized as AQ, okay, and it means dissolved in water. If we have salt water, and there are 5 grams of salt and 80 grams of water, we would know that the salt is the solute and the water is the solvent. And when combined, they make a solution. Okay. Couple more terms on this slide. Soluble versus insoluble. Something that is soluble is something that can dissolve. Insoluble is the opposite, so it does not dissolve. And things that are insoluble usually form a solid or a precipitate. Couple of more terms. We have miscible and immiscible. Miscible is something that can combine in any amount or any proportion. Where immiscible does not. Okay. Then we have a couple of diagrams here. The first one is just a picture of a solution showing you where the solute and the solvent are. Solutions can actually be any state of matter. We just tend to work with aqueous ones. And the lower picture describes solubility. Something with a high solubility is more likely to dissolve and break into its ions. Or something with a low solubility is more likely to form a solid. Let's move on. Now we're going to discuss solution formation. Okay. We primarily are going to focus on ionic compounds. When an ionic compound turns into a solution or is dissolved into solution, water molecules must collide with the ionic salt. Okay. This process is actually known as solvation. So that's the fancy word for it. Okay. The water molecules collide with the ionic salt and they have to overcome forces that exist between the ions. The oxygen portion of water is attracted to the cation. As review, cations are positive. And the hydrogen portion of water is attracted to the anion. anions are negative. If we look at our picture of water over here, you can see that the oxygen portion of water is partially negative, and the hydrogen portion of water is considered partially positive. And we know that opposites attract. Okay, so oxygen is negative, and opposites attract. And of course, hydrogen is positive, and again, opposites attract. The forces of water provide the energy to break the ionic bonds, and we like to say that the ions undergo hydration. If you look at this diagram here, you can see what's taking place with salt. So the salt is being bombarded with water, and the ions are breaking apart. If you look at sodium right here, you can see that the oxygen portion of water is surrounding that ion, just like we said. And if you look at the chlorine here, you can see that the positive portion, the hydrogen portion of water, is surrounding the chlorine. This is called solvation. And this is how solutions are formed. Let's discuss some properties of solutions. These are things you probably are fairly aware of, but let's talk about them anyway, just in case. One property of solutions is the rate of dissolving. There are a variety of factors that affect rate of dissolving: temperature, having smaller particles, and stirring. Okay. When temperature goes up, we know that the rate of dissolving goes up. So as temperature increases, the rate of dissolving will increase. Okay. A hot coffee is more likely to dissolve sugar faster than something that is iced or cold. The reason for this is because as temperature increases, kinetic energy increases. They are directly related. So the movement of molecules is increasing. And since the molecules are moving more, they're colliding more, they're more likely to come in contact with fresh solvent, and they dissolve faster. Okay. Smaller particles, things that have a larger surface area, also dissolve faster than things that are not quite as small. Okay. And I like to think about sugar and maybe a sugar cube for this one. So free sugar usually will dissolve a little bit faster than a sugar cube because the sugar cube is not necessarily all in contact with the water or whatever you're trying to dissolve it into initially. Okay. So the smaller particles are more available to the solvent initially. Since they're more available, they're going to dissolve at a faster rate. Okay. And finally, stirring increases the rate of dissolving. Okay, and again, that's something we know, right? If you stir something, it's more likely to dissolve than if you do not. And the reason for this is because you're helping those molecules move around, okay, or the salt move around, whatever you happen to be dissolving. And because you're moving them, okay, fresh solvent comes in contact with the solute, which increases dissolving. So they're moving particles come in contact with fresh solvent. And are therefore more likely to dissolve at a faster rate. Okay. Another property of solutions is conductivity. Sometimes solutions are going to be not conductive, and sometimes they will conduct. When a non-electrolyte is added to solution, such as a covalent compound which does not break into ions, it will not conduct electricity. Electrolytes, on the other hand, do conduct electricity, and there are two types. Okay, and salt will only conduct electricity when it's dissolved. We have weak electrolytes and we have strong electrolytes. Something that is weak, we like to say will have a dim light because they only partially ionize or break apart into their ions. And usually here, your weak acids and bases go. Okay. For strong electrolytes, you're going to get a very bright light. And that's because these substances 100% break into ions. Okay. And this includes things that are ionic, as well as your strong acids and bases. We'll cover that in more detail in a later PowerPoint. Here you have a diagram of each type of electrolyte. Diagram number 1 is for strong electrolytes because everything's completely broken apart. Diagram number 2 is for weak electrolytes because they're partially broken apart. And diagram number 3 is for non-electrolytes because they didn't break into their ions at all. We have some example equations that indicate when something is strong, weak, or non-electrolyte. They can be found below. HCl is a strong electrolyte, so when it's put into solution, all of it breaks into its two pieces. So it gets a single-sided arrow indicating that. Something like HF is a weak acid, so we use a double arrow to indicate that some of it is going to break into ions, a small amount, and some of it is going to stay together as a molecule. And finally, for non-electrolytes, even though this is normally not written, anything covalent is considered non-electrolyte. So we can draw C6H12O6, okay, and say basically that it stays C6H12O6 because it's not going to break apart. Okay. Moving on. Let's talk about solubility, another factor of solutions. You'll see here that I have defined some terms for you. Solubility is defined as the maximum amount of solute that dissolves in a given amount of solution, has units grams per 100 milliliters, or sometimes grams per 100 grams of water. There are 3 main types of solutions: saturated, unsaturated, and supersaturated. Saturated solutions have the max amount they can hold. So I often like to say that these are the just right solutions. Unsaturated have less than they can hold, so they're more diluted. And supersaturated have more than they can hold, so they're more concentrated. This graph shows you some solubility curves, and it can be used to figure out if something is saturated, unsaturated, or supersaturated. If something is saturated, it will be right on the line for that substance. If it's unsaturated, it will be below the line for that substance. And if it's supersaturated, it'll be above the line for that substance. So let's do a quick example. We're going to focus on KNO3, okay? So if we're looking at KNO3 and you're told at a temperature of 40 degrees, it's approximately 62 grams of solute. We're right on the line for KNO3 at that temperature, so that would be saturated. If instead you were told at 40 degrees that 50 grams were dissolved into solution, you would say, oh, it's below the line for KNO3, so it's unsaturated. And finally, if you were told there were 80 grams put into the 100 grams, it's above the solubility curve line, so it would be super saturated. We will continue our study of solutions in the next video.